Hello friends, welcome to engineering tutorial. Today we are going to extend our discussion on some of the basic and fundamental concepts related to electrical circuits. So here we are going to discuss some more concepts in relation to circuit theory or electrical networks. We are going to start this video with series and parallel combination of resistances. So first we are going to discuss series connection of resistances. So as you see in this circuit diagram, we have three resistors R1, R2 and R3 connected back to back with the tail end of one connected to the beginning end of the other. This is the series connection of resistors. Now these three resistances connected back to back are supplied from a DC voltage source V. Now we all know the current in a series connection of impedances or circuit elements stays the same. So the same current I flows through each of these resistors R1, R2 and R3. So now applying Kirchhoff's voltage law or KVL as we call it in short form, we can write as the net applied voltage V is equal to the voltage drop across each of the three resistances R1, R2 and R3. So V is equal to V subscript R1 plus V subscript R2 plus V subscript R3, where these three represent the voltage drop across each of the three resistances R1, R2 and R3. Now let the equivalent resistance of the circuit, taking into account all the three resistances, be equal to R subscript EQ, R equivalent. So we can write the applied voltage as I into Req, where I is the circuit current. Now as the same current is flowing through each of the three resistors, we can replace VR1 as I into R1, VR2 as I into R2 and VR3 as I into R3. So here IR equivalent is equal to I into R1 plus R2 plus R3. I on both sides, as they are same, get cancelled out. R equivalent is equal to R1 plus R2 plus R3. So we find out that the equivalent resistance of a series combination of resistors is equal to the summation or addition of the individual resistances. Next we are going to discuss about parallel combination of resistance. Now in this configuration, multiple number of resistors are connected with their two ends connected to the two terminals of a voltage source, one above the other. Here it's one above the other, but the main thing in a parallel combination of resistance is that each of the resistance have their two ends connected to the same two terminals of a voltage source. Here see, this resistor has its two ends connected to the two ends of the voltage source, same two ends of the voltage source. This has also got its two ends connected to the same two ends. This also has its two ends connected to the same two ends of the voltage source. So applying Kirchhoff's current law here, we can write it as the net current I divides itself here it divides itself here as I1 plus I2 plus I3. So I1 current flows through R1, I2 current flows through R2, and I3 current flows through R3. So we can write it down as I is equal to the net applied voltage by Req, where Req is the equivalent resistance of this parallel combination, which is equal to I1 can be substituted by V by R1, I2 can be substituted by V by R2, and I3 can be substituted by V by R3. Now the reason I am writing it like this, because the voltage across these parallel resistance are the same. The same voltage appears across R3, which is equal to V. V also appears across R2, across its two terminals, and also V is the terminal voltage across R1. So finally we can write the expression in this form: V by R equivalent is equal to V common from these expressions to 1 by R1 plus 1 by R2 plus 1 by R3. So VV gets cancelled on both sides, on LHS and RHS, so we get the expression in this format: 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Now next we are going to discuss about the series and parallel combination of inductances or inductors. Now here in this circuit we have two inductors, L1 and L2, connected to an AC voltage source, and these are connected in series, connected back to back. So same concept here. Applying KVL, we can write V is equal to the voltage drop across inductor 1 plus the voltage drop across inductor L2. Now we know that the voltage developed in an inductor is given by L into di by dt, where L is the coefficient of self-inductance and di by dt is the rate of change of current flow through the inductor. So here let the equivalent inductance of this series combination be equal to L subscript Eq. So we can write V as L Eq di by dt, and VL1 can be substituted by L1 di by dt, and VL2 can be substituted by L2 di by dt. As the same current flows through the series combination, the current remains the same here. So again, L equivalent di by dt, di by dt is common from these two, and we can write it as L1 plus L2 into di by dt. So the di by dt gets cancelled from both the LHS and the RHS, and we get L equivalent is equal to L1 plus L2. So we infer that in a series combination of inductors, the equivalent inductance is equal to the sum or addition of the individual inductances, same as resistance. Next is the parallel combination of inductors. Here two inductors are connected in parallel with their two ends connected to the same two terminals of the voltage source, AC voltage source V. Now here we can apply Kirchhoff's current law, as at this point the current divides itself. I is equal to I1 plus I2. Now we know the expression for current flowing through an inductor is given by 1 by L into integration of the applied voltage over a specific interval of time dt. So let Leq be the equivalent resistance of this parallel combination of inductors. So we can write the total current I as 1 by L equivalent integration of the applied AC voltage over particular interval of time dt. We can write I1 as 1 by L1 integration of V dt plus 1 by L2 integration of V dt. Now here the V remains the same as the terminal voltage across these two inductors are the same as they are connected in parallel. So in this expression the integration of V dt becomes common. So we can write 1 by L equivalent integration of V dt is equal to integration of V dt common into 1 by L1 plus 1 by L2. This term gets cancelled from both LHS and RHS, this integration of V dt term, and we get 1 by L equivalent is equal to 1 by L1 plus 1 by L2. So the equivalent expressions for both resistors and inductors is the same. Next comes the term of capacitors, series and parallel combination of capacitors. First is series combination of capacitors. Now here two capacitances C1 and C2 are connected in series across an AC voltage source V. First we apply Kirchhoff's voltage law. The net voltage, applied voltage V is equal to the voltage drop across capacitor 1 plus the voltage drop across capacitor 2. Now let C equivalent be the net equivalent capacitance of this series combination of capacitors, and I be the circuit current, as it remains the same throughout all the circuit elements, so that is capacitor 1 and capacitor 2. Now Vc1 can be substituted by 1 by C1 integration of I over interval dt, and Vc2 can be substituted by 1 by C2 integration of I over an interval dt. This is the expression for voltage developed across the capacitor terminals, 1 by C I dt. So this integration of I dt term is common in the LHS and RHS. It's taken common here, 1 by C equivalent integration of I dt plus integration of I dt into 1 by C1 plus 1 by C2. So this term gets cancelled and we get the final expression as 1 by C equivalent is equal to 1 by C1 plus 1 by C2. Now this is the opposite case as compared to resistors and inductors, where in series combination the equivalent impedance was equal to the sum of the individual impedances. Here it is the reciprocal. So it's quite the reverse of resistors and inductors. Now next comes the parallel combination of capacitances. Same thing, two capacitors are connected in parallel with their two ends connected to the same two terminals of the AC voltage source V, and first of all Kirchhoff's current law is applied at this point, where the net circuit current gets separated into two currents, I1 and I2. Now C equivalent is the equivalent capacitance of this parallel combination circuit. Now the voltage across each of the capacitors is the same as they are connected in parallel. Now the expression for current flowing for a capacitor is given by C dV by dt. So the circuit current can be substituted by equivalent capacitance C subscript EQ into dV by dt. The rate of change of voltage developed across the capacitor with respect to time equal to I1 can be substituted by C1 dV by dt. I2 can be substituted by C2 dV by dt. Now this dV by dt term is common in each of the LHS and RHS. So we can write and gets cancelled out. C equivalent is equal to C1 plus C2. Now it's just as I said, it's the opposite as compared to resistors and inductors. Next, we are going to discuss about energy sources. Now the energy sources which are connected in electrical circuit networks can be classified into two categories: direct sources and alternating sources. Now the direct sources are those whose magnitude or value doesn't change with time, whereas the alternating sources, and they do not change with time. Their magnitude and direction doesn't change with time. The direct sources are DC, whereas the alternating sources, their magnitude and direction changes with time. As simple as that. Now further, the direct sources can be classified into two categories: independent sources, where the strength of the voltage or current or the energy source remains unchanged by any variation in the connected electrical network. So any change in parameter in the circuit network has leads to no change in the strength or magnitude of the voltage or current. Now this is the symbol where the independent voltage and current sources are represented. This is the voltage source and this is the current source. By an arrowhead, here this is a positive and negative polarity inside a circle. This is an arrowhead which gives the direction of flow of current inside a circle. Next is the dependent source. It's quite the opposite to the independent. Here the strength of the voltage or current of the source is directly related to some parameter in the connected circuit. So this is the symbol of dependent voltage and current source. It's a triangular or a diamond shaped box, a symbol inside which there is a positive and negative sign for voltage, and here it's an arrowhead which is kept inside a diamond shaped or rhombus shaped symbol. Now dependent sources are of the following types. First is a voltage controlled voltage source, where the magnitude and direction of the voltage depends on some other voltage connected in the circuit. Current controlled voltage source, where a circuit current at some point in the network controls the magnitude and direction of the voltage. Voltage controlled current source, where the magnitude and direction of the current is controlled by some other voltage in the circuit. And current controlled current source, where the magnitude and direction of the dependent current source is controlled by some other circuit current flowing at any other point in the network. So these are some of the concepts related to energy sources. So here we are going to discuss about source transformation, which deals with conversion of a voltage source into a current source and a current source into a voltage source. So here it is the circuit diagram which represents a practical voltage source. It has a voltage source with an internal impedance or resistance RV, and hence as a result there is some voltage drop across this resistor, causing loss of voltage from the source. Similarly, this is the schematic diagram for a practical current source in which internal resistance is there in parallel, which causes loss of current from the source as per the current division rule. Now in both of these cases there is an imaginary load resistance RL connected for the sake of analysis of these two circuits. Mind you, this load resistance is not there physically, we have just connected here for analysis purpose. Now we are dealing with the conversion of this current source into this voltage source and vice versa. So in this case, this load current IL subscript V is equal to V by RV plus RL. V by RV plus RL. And in this case, the load current IL subscript I is equal to, as per the current division rule, this I into RI by RL plus RI. So in order for the two sources, that is the voltage source and the current source, to be called identical, the two load currents must be the same. So IL subscript V must be equal to IL subscript I. That implies V by RV plus RL is equal to I into RI plus RL plus RI. So, but here there is no physical load resistance connected. So this current is 0 and the entire current flows through this resistance Ri, and the terminal voltage across this end and this end should be the same. Here the terminal voltage is equal to V. So here too the terminal voltage around here is equal to V, which means that I into Ri is equal to V. So by substituting I into Ri with V, we get V by RV plus RL is equal to V by, this is V by Ri plus RL. So all the terms are equal here, V, RL, V and RL. The only different terms are RV and Ri. So the internal impedances of the two sources, that is the practical voltage source and the practical current source, are the same. So we can deduce that in order to convert a voltage source to a current source, we can convert it into this form. We replace the voltage source with a current source where the current is equal to V by R, and the current source with a voltage source where the voltage is equal to IR. And in this case, the series connected resistance is connected in parallel with the current source, and the parallel connected resistance is connected in series with the voltage source. So here I have discussed with you some more concepts related to circuit theory and network theory. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical and electronics engineering. Thank you very much. Have a great day.